Welcome to RSCH503, Research Methods and Biostatistics, a 3-credit graduate course offered by Drexel University College of Nursing and Health Professions. Probability theory addresses statistical analysis as the likelihood of accurately predicting an event or the extent of an effect. The following idea of probability is simple. The probability that an event, object, or person will occur is equal to the relative frequency of occurrence of that event, object, or person in the population under consideration. Probability is expressed as lowercase p, with values expressed as percentages or as a decimal value ranging from 0 to 1. The p in statistics is the probability that a particular outcome may have occurred by chance. If a statistical test determines that a finding occurs at a p-value of 0.01, it may be concluded that there is a 1 in 100 probability that that finding occurred by chance, or a 99 in 100 probability that the finding is a reliable one. Another way to define probability is this. P is the probability of rejecting the null hypothesis when the null hypothesis is actually true. Recall again that the null hypothesis is a mathematical statement to the effect that there is no difference between specified population parameters, or a statement to the effect that there is no relationship between the independent and dependent variables in the population under study. Classic hypothesis testing refers to the process of testing a hypothesis to infer the reality of an effect. Hypothesis testing begins with the null hypothesis. An investigator then establishes the values of two theoretical probabilities. First, the alpha, or Greek letter alpha, is set. Alpha is the probability of rejecting a true null hypothesis. Alpha is known as a type 1 error. Second, the beta, or Greek letter beta, is the probability of retaining a false null hypothesis. The researcher sets the value of alpha. The beta is a theoretical construct, and its value is seldom known in the practical research situation. However, it is known that type 2 errors are more likely to occur when the sample size is too small or when the alpha is set too rigorously. The more one guards against a type 1 error, the greater the likelihood of a type 2 error. The consequences of a type 2 error may be great or small, depending on what truth is lost due to an erroneous non-significant finding. Statistical hypothesis testing follows an organized outline. First, the investigator states the primary null hypothesis. Second, the study alpha is set. Quite commonly in nursing research, the alpha, or p, probability value is established at either 0.01 or 0.05. 3. The researcher may also establish a beta value. Again, in nursing and behavioral sciences, beta is commonly set at 0.20. A beta at 0.20 means that the researcher will allow for a 20% or lower chance of making a type 2 error. 4. The researcher then conducts a power analysis. We will have more on this in this session. 5. The researcher designs and then conducts the study. 6. Statistical analyses are conducted. 7. The statistical significance of the findings are then determined. And finally, 8. The null hypothesis is either accepted or rejected based on the statistical significance of the findings. If the null hypothesis is rejected, then the alternate hypothesis is accepted. What is power? How is power defined in statistics? The power of a statistical test of some hypotheses is defined as the probability of correctly rejecting the null hypothesis. Or consider power as the probability that a statistical test will detect an effect when it actually exists. Recall that effect size is the degree to which the phenomenon of interest is present in the population, or the degree to which the null hypothesis is false. Power is calculated as 1 minus beta, the inverse of type 2 error. For example, if the beta is set at 0.20, or 20%, then the power of the planned statistic has been set at 0.80, or the statistic will have an 80% chance of detecting an effect if it actually exists. In the previous in the previous session, we indicated that Step 4 of statistical hypothesis testing was to conduct power analysis. As a brief review, let's discuss the parameters of power analysis. First, power is a function of the significance level chosen. This is noted as lowercase p. Again, the alpha chosen or the type 1 error accepted. Second, power is a function of the sample size, or n. And third, power is also a function of just how false the hypothesis really is, or the degree to which the phenomenon is present in the population, or the degree to which the null hypothesis is false. Tools are available to researchers to calculate power. It is important that power be achieved and reported in study findings. This is particularly true if the study fails to reject the null hypothesis. That is, a non-significant finding is reported. If the power is high, the finding is strengthened. The figure on this slide, taken from page 521 of your text, illustrates the relationships between type 1 and type 2 errors. Particularly note what is labeled as the decision column, which speaks to type 1 error and type 2 error. It is always important to remember that statistical significance and clinical importance are separate ideas. In fact, research findings that are statistically significant may not be truly clinically important. Closely aligned to statistical significance is the notion of inference. As you know, a statistic is obtained from a sample, for example, a sample mean or standard deviation. A parameter is a true but unknown numerical characteristic of a population, for example, the population mean or mu. A key concept in statistical analysis is the movement from a sample statistic ultimately to the population parameter, inferring from a specific concrete finding obtained from a sample to an abstraction. Basically, there are two categories of statistics. First, descriptive statistics that includes both measures of central tendency, mean, median, and mode, and measures of dispersion, range, standard deviation, and variance. Second, inferential statistics, which includes both parametric and non-parametric statistics, are described on the next slide. Statistical knowledge and skills are powerful instruments in your toolbox, just as powerful and important as your other tools, such as the stethoscope, physical examination techniques, and others. Proper use of statistics will enable you to care for individual patients while simultaneously being aware of your populations of interest. Evidence-based research is grounded in proper use of statistics as a tool. As noted previously, descriptive statistics includes both measures of central tendency and measures of dispersion. Inferential statistics further divides into parametric and non-parametric. With parametric statistics, findings are inferred to parameters of normally distributed populations. Parametric statistics are used with continuous variables on an interval or ratio level of measurement. Non-parametric statistics are used with non-normal distributions and with ordinal and nominal data. There are several practicalities of data analysis to consider in research. One practical aspect is the need to, quote, clean the data, indicating that data printouts need to be reviewed for errors prior to running analyses. Another is to identify missing data. While missing data may be coded numerically as 999 or some other value chosen by the investigator, printouts need to be reviewed for errors in this area also. Can the investigator recode data to create new variables? Statistical software programs have capabilities to transform, recode, or compute new variables, actions that investigators may become aware of as they review data printouts. And as you can well imagine, investigators must carefully store data on backup files for security purposes. Descriptive statistics literally describe the sample. For each variable in the study, descriptive statistics, both measures of central tendency and measures of dispersion, can be calculated. Such descriptive statistics tell an investigator who the subjects are. These are the subjects in the normative sample. In this slide, we see an SPSS frequency table of 3 variables: gender of child, girl or boy, nominal level; does the mother smoke, yes or no, nominal level; and prenatal care, none to low to moderate to high, ordinal level. This snapshot shows the frequency, percent, and cumulative percent of each variable. A confidence interval is the range in which the value of a population parameter is estimated to be, or when the probability of including the value of the parameter within the interval estimate is known. This is referred to as the confidence interval. Confidence intervals consist of a range of values, or interval, that act as good estimates of the unknown population parameter. However, in infrequent cases, none of these values may cover the value of the parameter. It does not describe any single sample. This value is represented by a percentage, so when it is said that a researcher is 99% confident that the true value of the parameter is in the confidence interval, this expresses that 99% of the hypothetically observed confidence intervals will hold the true value of the parameter. After any particular sample is taken, the population parameter is either in the interval realized or not. It is not a matter of chance. The researcher sets the desired level of confidence. If a corresponding hypothesis test is performed, the confidence interval is the complement of respective level of significance. That is, a 95% confidence interval reflects a statistical significance level of 0.05. The confidence interval contains the parameter values that, when tested, should not be rejected with the same sample. Confidence intervals are commonly stated at the 95% confidence level. Once data is analyzed, it is important that a researcher consider conducting post hoc analyses. Post hoc analyses are commonly conducted in studies with more than 2 groups when the analysis indicates that the groups are significantly different but does not indicate which groups are different. Post hoc analysis will reveal what the differences are. How do the groups differ from each other? Post hoc analysis frequently results in insights that generate further research. This presentation was prepared for graduate nursing students at Drexel University, College of Nursing and Health Professions. The primary book used in this research course is The Practice of Nursing Research, Appraisal, Synthesis, and Generation of Evidence, 2017 edition, by Jennifer R. Gray, Susan K. Grove, and Suzanne Sutherland. This book is published by Elsevier Saunders, St. Louis, Missouri.